everyone. It's a pleasure to be again at Q2B. Thank you, Matt and JB and Sandrine and the entire QuEra team for doing so much to bring the community together. And this is me. Very good. So today, I'm going to give you a progress report. This is like a parent-teacher conference. I'm going to tell you how well we did in 2024 and what we're up to. So first, a little bit about QuEra. We're headquartered in Boston, close to MIT and Harvard. The closeness is not just geographical, but also philosophical. There's a lot of collaboration between MIT, Harvard, and QuEra, and we enjoy both the steady stream of postdocs that come out of that, as well as the fantastic innovations that are happening in Misha Lukin's lab and in many other labs. We build quantum computers using neutral atoms, and I know I get paid to say that, but I truly believe that this is the best way, the most promising way to get to fault-tolerant, large-scale quantum computers. And Professor Preskill mentioned that, I think, at least in his opinion, Rydbergs are a very good candidate to get there. Our first machine, Aquila, has been online on Amazon Bracket since November of 2022. 2 years now, 130 hours a week, hundreds and hundreds of users, dozens of countries, many publications. And we believe that we are the scientific and as well as the commercial leader in neutral atoms. And like many of you, we focus on creating commercially useful, large-scale, fault-tolerant quantum computers. Why neutral atoms? For those that need a refresher, neutral atoms can scale to thousands or tens of thousands of qubits on a single machine, which makes it easier to get to more logical qubits. Neutral atoms operate at room temperature. You don't need cryogenic cooling and all the complexities that come with it. Neutral atoms we can shuttle the qubits. We have all-to-all connectivity, and that allows us to implement both algorithms as well as quantum error correction that's not available in static qubits. High fidelity, long lifetime. Maybe a few years ago, neutral atoms were behind other modalities, but that's not the case today. I think we like to say that neutral atoms went from the dark horse to the workhorse of quantum computing. And these are natural qubits. We can take 1 billion qubits, and they'll be perfectly identical. There are no manufacturing defects. So last year on this stage, I had the honor of presenting unique results led by Harvard with participation with QuEra and MIT and NIST and several others that spoke about complex algorithms using 48 logical qubits. And modestly, I think that generated a little bit of an earthquake in the industry. We've had customers that come to us and say, we always thought that quantum would be 5 years away, but now based on the results from Harvard and QuEra and others, we think it's actually shorter. We think it's maybe 3 years away if you've made significant progress for us. So just to recap what we showed last year, the team implemented a complex sampling circuit with an 832 code block, 48 logical qubits, and CCZ gates. We showed that by increasing the code distance, the error rates go lower. We prepared color code qubits, and we demonstrated fault-tolerant creation of logical GHZ states. A year ago, that was a big deal. I think it's still a big deal today, but in this past year, we've seen some fantastic results from Google, from Quantinuum, and from others. So I think we're all sort of moving into the area of, yeah, we can do quantum error correction. This is how it looks, other than the title of the slide that's a little bit off. We employ a zoned architecture. We have an area of storage where qubits have long lifetime. We have an entanglement zone where we can shuttle qubits there, and then a measurement zone where we can actually measure the results. And this video shows you one of the algorithms, and these are actual atoms. Of course, they're not in a quantum state because to make the video they would not be, but this is how it looks. So what have we done since? Ooh, the fonts are bigger than I remember them. So I think the quantum computer hardware industry has gone through sort of 3 phases. Initially, maybe 5 or so years ago, we were wondering whether quantum computers could be created at all. I mean, the clicker that I hold in my hand, although it's obviously made of material that has quantum properties, behaves like a classical object. There's 0 chance that it's in my room right now as opposed to in my hand. But once quantum computers were created, the next thing was, can quantum error correction work? Because if quantum error correction does not work, then we are unable to do long calculations, which are important to solve the problems that we really care about. Well, we and others have shown that quantum error correction does work. And so now we're in this third stage of how fast can we scale to truly useful quantum computers. And again, the progress in 24 and earlier, I think, leads many to believe that useful quantum computers, for some applications, maybe just a few short years away. So the scientific progress, one report, one paper that I want to talk about a little bit, is the usual knock on neutral atoms is, are they slow? Because the gate speed is comparable to superconducting, but if you want to shuttle qubits around, the qubits are a few microns apart, and you move them at approximately a meter a second. So the movement, actually, the shuttling takes time. And this is a graph from a Microsoft work, I believe, that analyzed factoring in quantum chemistry and other applications and showed how much time would actually be required to do it. And so with 100 microsecond gates and 100 microsecond measurements, large algorithms might take almost a year. That's not good. So a couple weeks ago, we released a report, a paper that was led by QuEra with participation from Harvard and others, that spoke about algorithmic fault tolerance. And what it essentially does, it drastically reduces the cost of fault tolerance. And the basic idea is very simple. Implementation, I'll leave that to the scientists, but the basic idea is rather simple. Instead of protecting the quantum state after every quantum operation, we look at algorithmic blocks. I mean, after all, you do a certain number of gates, and then you do measurement, and then you use this measurement to do feed forward to decide what are you going to do next in the algorithm. So instead of conventional fault tolerance, that you're trying to protect individual operations, here we're trying to protect algorithmic blocks. And what that results, forgive the math, in the first approach, in the conventional fault tolerance, you're doing an order of D extraction, D meaning the codistance, whereas in algorithmic fault tolerance, you're doing an order of 1 syndrome extraction rounds per operation. And what that means for reasonable code sizes, that could be a 30x improvement, 30x speed up in the time to reach the result. And if you think a little bit about the intuition behind it, again, we're protecting the classical measurement instead of the individual quantum operations. This is possible in neutral atoms because neutral atoms have this capability of transversal gates. Essentially, you can take a logical qubit, try to put that in the clicker in my pocket and not forget where it is. If you take one logical qubit here with 5 physical qubits and you take another one here, we can overlay them essentially one on top of the other, and then we can do a gate operation on each physical qubits simultaneously, thereby performing that same operation on the logical qubit. And that is something that doesn't happen, of course, in static qubit configuration. In static qubit configurations, you have a much more probability that an error starts spreading out if you're doing lattice surgery or something else. So this is a unique capability of movable atom architectures like neutral atoms, and we think it is compatible with universal quantum computation. We want to do all kinds of gates. We want to create a universal circuit, and this approach supports that. So in our analysis, that 30x improvement, and we've started looking at some algorithms and implementing them that ways, a 30x improvement can take a month and turn it into a day, or it can take a year and turn it into approximately 2 weeks. So essentially, it's a way to compensate for the slowness or the relative slowness of moving the atoms, and therefore we think that now we've addressed a key impediment to using neutral atoms and made them on par with superconducting or others, while still having all the other advantages that we discussed, perfect qubits, no cryogenic cooling, all-to-all connectivity, and so on. Let's talk about commercial progress. What have we done commercially since we spoke a year ago on this stage? First, we continue to enjoy the availability of our 256-qubit analog computer on Amazon Bracket. We went from 2 years ago, it was 10 hours a week in terms of availability. Now it's 130 hours a week, so really have no excuse. If you got a credit card or a Bracket account, you can use it pretty much on demand. And people use it for simulation and optimization and machine learning, and we've seen plenty of papers that use it and generate some fantastic results. 3 additional milestones. The most recent one is that Google made a strategic investment in QuEra, which by itself is interesting, right? Google is doing all these amazing things with superconducting qubits. Why do they need to invest in the neutral atom company? I'm not going to give you the answer. You're going to have to ask them, but I think you can guess. The other question I get asked is, how much money did they invest? And the answer is they had a truck with quarters, and we're still counting the quarters, and I think we'll finish counting the quarters in a couple of weeks, and so we'll tell you all next month or so exactly how much money we got from Google, and as well as other investors in that round. Additionally, we announced the sale of 2 machines. The first one was to AIST. AIST is the National Institute of Standards in Japan. They bought a neutral atom machine from us, a digital gate-based neutral atom machine. They paid, I think we announced something on the order of $42 million for that. And then we also won an award to deliver a neutral atom testbed to Harwell, part of the UK National Quantum Research Program. Both these systems are in the process of being delivered. I think half the AIST computer is already in Japan. The other half is coming very soon. And in Q1, we'll have in Q1 25, we'll have both the Japan computer in Japan as well as the UK testbed in the UK as well. This is the gate-based computer. So we used similar technologies, with some changes, the zoned architecture that I described, to do a gate-based neutral atom with 256 qubits. Interestingly, at AIST in Japan, it's going to be installed alongside a classical supercomputer called ABC-IQ. I think it has 2,000 H100 GPUs. They're going to use it both for hybrid quantum classical applications as well as high-performance simulations. So we look forward to integrating both the quantum and the classical. When we go to HPC centers, and they'll talk about megawatts, and I know they're talking about setting up nuclear power plants to power their HPC centers and supercomputers. We say, well, do you think you have 7 kilowatts to spare for us? And they say, 7 kilowatts, I can put that in my living room. And so that's about what this computer takes. And of course, it's not universally powerful as all the supercomputers, but there's a set of problems that it can probably solve faster than them. And when we deliver a computer, we also provide on-premises installation support and maintenance. So you don't just get the car, you get the driver as well, so to make sure that you can make maximum use of your asset. The other thing we realized in 2024 is that it takes a village. We continue to grow. We're about close to 80 people right now, but we cannot be experts in everything. We cannot be everywhere. We cannot do everything that's necessary to deliver value or immense value to the customers. And therefore, we started the QuEra Quantum Alliance. And you can see all these amazing partners from Classic to Blue Qubit to QBraid. Just today, we announced that Algorithmic, the chemistry algorithm company, has joined the Quantum Alliance. And we basically work together to both educate and provide value to customers around the world. And if you're interested in being part of the QuEra Quantum Alliance, then just join us, QuEra.com/partners. So this is a high level of what we've done in 2024. And the next question is, well, what's next, right? What am I going to talk about in 2025, or whoever will be here on stage? So the first thing that we want to talk about and we're working on is compilers that take advantage of that neutral atom architecture. And what I mean by that is that even if you gave us, say, a QASM circuit, the work doesn't end there. Neutral atoms allow parallel gates to, parallel operations to happen at the same time. So what you see, for instance, on the video is a simulation of atoms moving from the storage area to the entanglement area. We move them in such a way that when they're close together, we can entangle them. So there's a lot of work on how to optimize these circuits, how to make use of the parallelism, how to move the atoms in the best possible way. I mean, if you drive a car and you drive it too fast on a turn, it's going to fly off the road. Well, we don't want the atom to fly off the tweezer or to lose coherence. And so there's a lot of work that happens from the quantum assembly all the way to pulse level. And this is also an area where we expect to work with many industry and academic partners to really deliver the best possible solution. And going back to super large fonts, if I look back at the where quantum hardware is and where quantum software is. So we spoke about quantum hardware being, can we make a computer, can we do QEC, and how fast can we scale? In our opinion, the software is staggered a little bit, sort of half a phase after that. So once you can build a computer, you probably want to write a sort of hello world program to say, okay, can I write something that even simplistic runs on that computer? Once QEC can work, and now we've got these computers with 50 or 100 logical qubits and a couple hundred physical qubits, we believe we're entering this area of co-design. I'll talk about that in a little bit, but co-design basically says we're going to work really, really closely between the algorithm and the hardware to make sure that we extract the maximum juice out of the qubits or out of the computer. And then if we had really, really large-scale computers, then we need tools, software tools that scale. Again, I mentioned Classic, Ryzen, and others are working on making it much easier, and CUDA-Q, of course, to make it much easier to write efficient quantum programs. And so we announced the algorithm co-design program, and one customer that we announced for that is Los Alamos National Labs. They're doing a sort of a 2-year project with us to take one of the problems that they really care about and optimize it to our computer. And the inspiration that we had was the Apollo 11 onboard computer. So the Apollo 11 onboard computer obviously took 3 people to the moon and back and returned them safely. And it had 70 kilobytes of ROM. That's all, 70 kilobytes of ROM. Do you think the software was written in MATLAB, in JavaScript? It's probably written in assembly language that was super hard-coded and optimized to take advantage of the limited resources of the computer. So so as much as we like our computers, we understand that they still have sort of limited resources in terms of number of qubits and the depth of the circuit. So we do this work that basically tries to choose the algorithm together with the customer to do tailored algorithm design and development, to run it on a simulator, and we're starting to release to early users a simulation of our digital quantum computer with an effective noise model and all the things that go behind it. And then we give them priority hardware access. Now that the machines are coming online in 2025, our gate-based machines, they can run these algorithms sooner. And of course, beyond that, we continue to work on our next generation, 3rd and 4th generation computer. Here's a little video. And at some point, someone stopped me from going sort of deeper into the optical table and showing all the magic that's happening there. But it is built. If you are in Boston, we'd love to have you. We'd love to show you some amazing hardware and software. And in closing, and just to leave a minute for questions, we believe that the future of quantum is closer than you think. We've made so much progress, both us as well as companies like Quantinuum and Google and others, and we've surveyed the industry not too long ago, and I think the general consensus is that it does move people faster than people have expected. So for that, thank you very much. We'll be available at the QuEra booth to take additional questions after this.